Have you ever found yourself just marveling at the sheer complexity, but also the effortless flow of a city's transportation system? Maybe you're on a subway line, right?
Yeah.
The train arrives precisely on schedule, the doors glide open, shut with that like reassuring hiss, and you're whisked away smoothly, efficiently. It's truly a testament to incredible engineering, isn't it? Thousands of people move day in and day out with seemingly invisible precision, but then, well, there's that moment. That sudden jolt, maybe the train grinds to a halt between stations, the lights might flicker, and a disembodied voice announces an unforeseen delay.
Right.
And just like that, that marvel of reliability feels, well, anything but. So for you, whether you're an aspiring engineer, an early career professional, or maybe just fascinated by what keeps our world moving, how did the brilliant minds behind these systems actually ensure they run so incredibly reliably, available precisely when we need them? And how on earth do they even begin to quantify what reliable or available truly means in a measurable, verifiable way? Welcome to The Deep Dive, the show where we take on big, complex topics, pull back the curtain, and break them down into digestible, genuinely fascinating insights. Today, we're plunging headfirst into the intricate world of using powerful statistics to ensure the reliability, availability, maintainability, and safety, or RAMS, as it's universally known in the industry, of our crucial transportation projects. We're talking about the mathematical bedrock, the invisible blueprint that keeps our trains running, our signals green, and our commutes as smooth as possible, well, most of the time.
And this topic isn't just challenging, it's absolutely critical, especially when you look at railway systems. I mean, think about the scale involved. We're talking about vast networks, sometimes stretching for hundreds, even thousands of kilometers. Then there's the non-negotiable demand for safety. I mean, moving thousands of people at high speeds means there's basically zero room for error. And finally, these are projects designed for decades, sometimes even, well, a century of operational life. What truly elevates the complexity, though, is that you're trying to make sense of incredibly rare events, a specific component failure, for instance, across literally thousands of interconnected moving parts, all while ensuring continuous operation. It's a monumental undertaking in probability and sophisticated risk management.
That is a huge challenge, isn't it? Trying to
Yeah.
predict something so rare across such a massive system and then actually guarantee it somehow. But before we even get to the predictions, we have to grapple with something maybe even more fundamental. What are we actually defining when we talk about reliability or availability? Because without that precision, you're almost guaranteed to run into problems down the line. What's the very first step the industry takes there?
Well, the very first step is really acknowledging the unique characteristics of public-guided transportation. These systems are inherently designed for extraordinarily high levels of technical reliability, just built that way from the start. And that inherent reliability, it directly translates to very high operational availability for the customer, for you waiting on the platform. Most of the time, your local subway or train runs without a hitch, right? That's kind of the baseline expectation.
Right, but, and this feels like a significant but, we're seeing an ever-increasing layer of complexity added to these systems. Think about the levels of automation now involved, the intricate technical interfaces between different subsystems, often from various suppliers, and the growing, relentless focus on life cycle costs, meaning not just the upfront price, but the total cost of ownership over, decades.
Yeah.
This evolving landscape means that a casual, sort of intuitive understanding of what reliable means just isn't good enough anymore. Not for planning, not for building, certainly not for contracting. You need utterly precise definitions for RAMS requirements, written down, understood, agreed upon by everyone involved.
That's precisely where we often see the friction, or sometimes even outright disputes emerge.
Yep.
You have the equipment consumers, the railway operators, the folks running the trains every day, and then you have the suppliers who design, build, and deliver the components and systems. These disagreements, they almost always stem from a lack of precise, contractually defined terms. What exactly does technical reliability mean for this specific component? How do we measure availability for the entire line? How do we demonstrate these requirements over a limited period, say the first 3 years of operation? And how do we break down those overarching system requirements to individual subsystems? Intuition, while helpful for a general understanding, it simply isn't sufficient when, millions of dollars in public trust are on the line.
Yeah, it's just like that car analogy, isn't it? You go to buy a new car, and you tell the salesperson, I want a reliable car. Oh, okay, what does that really mean? Does it mean it will never break down? Probably not. Or does it mean it won't break down more than once in 5 years? And if it does break down, how quickly will it be fixed? For your personal car, it's an annoyance, maybe a missed appointment. But for a train system carrying thousands, potentially tens of thousands of people an hour, That intuitive understanding absolutely will not cut it. You need hard numbers, clearly defined thresholds, and a method to prove it.
Exactly. To really drill down into these core concepts, let's start with a very simple example. Think about a limit switch on a train door. It's a small, unassuming component, but absolutely critical, right? It signals to the train control system whether a door is open or closed, ensuring safety and proper operation. Now, in transportation, these kinds of elementary components are typically engineered with the highest quality materials, designed to function correctly for many, many years. However, no component is perfect. From time to time, one might fail to perform its intended function. For our purposes here, failure simply means any unintended behavior. Maybe it gives a false signal or it just ceases to function entirely. So if our limit switch stops signaling door closed when the door is closed, that's a failure. Simple as that.
So you're essentially tracking these things minute by minute, almost like a medical chart for each component. If a limit switch, for example, is humming along, working fine, that's its uptime. We'll call it two, right? But then it inevitably fails at some point, and that's the start of its downtime, Delore, until it's fixed or replaced. Is that the fundamental rhythm we're looking at here? What are the key numbers that emerge from watching this cycle over and over again for countless components?
Precisely. That's the core cycle. If you were to observe just one of these components over a very, very long period, through many failures and repairs, you'd begin to build a clear picture of its working and non-working intervals. From that data, we derive some crucial parameters that underpin all of RAMS.
Okay, first up, let's talk about reliability. We derive key metrics directly from that uptime we mentioned. The simplest is mean uptime, or MUT, which is, well, quite literally just the average amount of time a component works correctly before something goes wrong. Closely related and absolutely fundamental is mean time to failure, or MTTF. This represents the average time a component works properly from the moment it starts operating until it fails for the first time. It's a measure of how long you can expect it to last before its first hiccup, basically. Now, you'll also hear a term that often causes confusion: mean time between failures, or MTBF. Here's the key difference, and it's really important to clarify this. MTBF is actually the MTTF plus the mean time to repair, or MTTR.
That's the crucial addition.
Right. MTTR is the average time it takes to restore or replace a component after a failure, getting it back into service. This MTTR is also sometimes referred to as the repair rate, denoted by the Greek letter mu, which is just 1 divided by MTTR. In practice, though, the difference between MTTF and MTBF is often negligible for most railway components. Why? Because MTTF values are usually incredibly high. We're talking tens or even hundreds of thousands of hours, while MTTR values are very short, maybe just an hour or a few hours. So, 100,000 hours versus 100,001 hours isn't a huge practical distinction, which is why MTTF is often the preferred metric when discussing inherent component longevity.
That's a great point about the practical equivalence for many railway systems. It simplifies things, and instead of mean time, sometimes engineers find it more intuitive or just easier to talk about rates. So the failure rate, usually denoted by lambda, is simply the reciprocal of the MTTF. So lambda equals 1 divided by MTTF. If your MTTF is, say, 100,000 hours, your failure rate is 1 divided by 100,000, or 10 to 5 failures per hour. Whether you use MTTF or failure rate, they all fundamentally describe the component's capacity to reliably serve its function. This intrinsic capability is what we refer to as its reliability, RT. RT specifically is the probability that a component is still working unfailed at a particular time pack. Conversely, failure probability, FT, is the probability that a component has failed by time t. They're two sides of the same coin. If RT is 99%, then FT is 1%.
And while we've been simplifying failure so far to mean any unintended behavior, in the real world of transportation, engineers and operators are often most interested in failures that actually impact the intended service for passengers. Maybe a minor sensor glitch doesn't stop the train, but a door not closing certainly does.
Yeah.
These service-affecting incidents are a subset of all possible failures, so the average time between them is naturally longer than the general MTTF. This more operationally relevant number is often called mean time between service failures, or MTBSF. It's what truly matters to the person waiting on the platform, you could say. It's also crucial to remember that these parameters, MTTF, MTTR, failure rates, they don't just apply to single tiny components like our limit switch, they apply to higher level aggregations too. Entire assemblies, complex modules, or even large subsystems like a train's entire communication system. And the more complex the entity, the more potential failure modes you have to consider in that aggregated number.
Exactly. And building on that, the next critical parameter, and one that resonates most with the end user, is availability. For an operator, for a passenger, the availability of the service function, meaning, is the train running when I need it, is far more relevant than just the technical reliability of an individual switch. Availability A is essentially the ratio of the average effective uptime to the total time that's uptime plus downtime. The formula for availability is A equals MUT, MUT plus MDT, or more commonly, A equals MTTF, MTTF plus MTTR. You can also express it in terms of those rates we just talked about, A was plus MTTF. And conversely, unavailability U is simply 1 minus availability. So if your availability is 99.9%, your unavailability is 0.1%.
Okay, now, while that formula looks pretty straightforward on paper, I imagine the practical realities of defining and truly measuring availability are a bit trickier. For one, selecting the appropriate MTTFs for complex aggregated subsystems can be really nuanced, right? Which failures truly count as service affecting? What about a false alarm that doesn't stop the train but causes a brief operational pause? And the definition of MTTR gets complicated too, I bet. For an operator, MTTR often means mean time to restore operational service and keep passenger traffic flowing, not just the pure technical repair time. This restoration might involve operational actions like rerouting trains or sending staff to manually clear a section, not just a technician fixing a circuit board.
And here's a subtle but profoundly important point. A and U are ratios, percentages. So even if the values are very high, say, a system achieves 99.99% availability, which sounds fantastic. A single failure event, when it does occur, can still have a disproportionate impact on perceived passenger service. That tiny 0.01% unavailability when it translates to a packed platform during rush hour means frustrated commuters and a disrupted schedule. The numbers might look great on a spreadsheet, but the lived experience can be very different.
Yeah, that makes sense. It also creates a bit of a responsibility split, doesn't it? The supplier of the equipment typically guarantees the technical MTTF, how long their gear is supposed to last before breaking.
But the operator is the one controlling the MTTR, how quickly that gear gets fixed and service restored through their maintenance crew, their staffing levels, their operational procedures. So if availability dips, who's ultimately responsible for the overall outcome? It's kind of a mixed bag, which must make contractual agreements very challenging. And finally, because unavailability is designed to be a very, very small number, we're talking about incredibly rare events. Demonstrating it accurately requires incredibly long observation periods. You need to see a lot of operating hours to prove a truly low unavailability, which can be difficult in a project timeline. Right. To further understand how we model these component failures, we need to introduce the crucial concept of the constant failure rate and the famous bathtub curve. If you look at how a typical component's failure rate behaves over its entire lifetime, it almost always follows this characteristic bathtub shape.
Okay, I think I've seen this before. Imagine plotting failure rate against time, right? In the very beginning of a component's life, say right after it's manufactured and installed, you often see early failures, sometimes grimly called infant mortality. This phase has high but rapidly decreasing failure rates. These are typically due to initial design flaws, manufacturing defects, maybe even issues during installation. It's like breaking in a new car, you might discover a few quirks right away.
Exactly. Then, after that initial shakeout period, you hit a long, stable plateau. This is the critical phase of constant failure rate. Here, the probability of failure remains surprisingly consistent over time, regardless of how long the item has already been working. There are no significant aging effects primarily influencing the failure rate during this phase. It's more about random events or external stresses causing failures. This is the phase that engineers are most interested in because its statistics are relatively accessible and, crucially, predictable.
And finally, at the very end of a component's designed life, you see the failure rate start to climb sharply again. This is the wear and tear phase. This is where components are simply aging, degrading, and eventually failing due to material fatigue, corrosion, or just simple exhaustion, like an old appliance finally giving up. But for most of the operational life, especially for complex electronic or electromechanical systems in a railway, things like control circuits, sensors, communication modules, engineers can often operate within that constant failure rate plateau, right?
That's generally the assumption, yes. And what does a constant failure rate truly mean? This is where the magic happens for engineers, statistically speaking. It means that the probability of a still working or just repaired item failing in a given time period is the same in every such period. If it fails and is replaced or repaired, the probability of it failing again in a similar future period remains constant. Think of it this way. If a component has a constant failure rate, it's like flipping a coin that never changes its odds no matter how many times you flipped it before. This isn't always intuitive, we expect things to wear out. But for many complex electronic systems and railways, this assumption holds true for most of their operational life. And because it's true, engineers get a kind of statistical superpower. The math becomes incredibly predictable. They can use something called the exponential distribution for survival probability. This is like having a, well, not quite a crystal ball, but a very good statistical model for reliability. It means if a component doesn't fail in the first hour, its chance of failing the next hour is exactly the same. This vastly simplifies forecasting, maintenance schedules, and spares management because you don't need to track how old each individual component is, you just need to know its constant failure rate. It's a massive simplification that makes managing complex systems feasible.
Okay, so we've got these precise definitions, MUT, MTTF, MTTR, availability. And this idea of a constant failure rate simplifies a lot. But here's the kicker, and I imagine this is where the real challenge for engineers comes in. How do you actually prove these incredibly low failure rates in the real world? It sounds almost impossible to measure something that rarely happens, especially when you're dealing with hundreds or thousands of components across a whole line.
It absolutely would be impossible if you only had one component to look at. Think about it. How do you practically measure a specified failure rate, like, say, 1.25 times 10 to the minus 6 failures per hour? That's a tiny number. If you only had a single component, operating it for a typical demonstration period of maybe 3 years, which is about 25,000 operating hours, means you would statistically expect to see only 0.03 failures. You literally need over 100 years of continuous operation to expect just one failure from that single component. Clearly, that's not a practical timeline for any railway project.
Right, okay. So we're not talking about waiting a century for a single data point. Shoot. This is where the sheer scale of modern transportation systems actually comes to our rescue, isn't it?
Precisely. Reliability-critical components are almost never implemented as single units. They're typically deployed in batches of hundreds, sometimes even thousands, across an entire network or fleet. Take a track-mounted positioning transponder, often called a balise. If it has that very low failure rate of 1.25 to 10 to 6 failures per hour, and a high-performance train localization system might require, say, 5 of these balises between any 2 station tracks. So for a medium-sized subway line with maybe 40 station tracks, you could easily have around 200 balises installed. Now suddenly, over those same 3 operating years, you would expect about 5 failures across all those 200 balises.
Okay.
That makes measurement not only feasible, but statistically robust enough to draw meaningful conclusions. It's like trying to count a rare bird. You might not see one in your backyard, but if you're watching a whole national park, your odds go way up.
That's a great analogy. And this brings us neatly to the power of the Poisson distribution. When you have many identical components, and each component has that constant probability of failure we just discussed, the number of observed failures over a specific period of time doesn't behave randomly. It actually follows a predictable pattern described by this Poisson distribution. The key parameter in this distribution is mu, which represents the expected number of failures. And you calculate it quite simply, right? By multiplying the number of components n by their individual failure rate and the total time period. Mu is mu.
Exactly. What's truly fascinating and powerful here is how the Poisson distribution allows engineers to effectively convert the collective operating times of multiple components into observable, quantifiable event numbers, that is, specific counts of failures. It simplifies a very complex reality into a manageable statistical model. Now, when you're using this for system acceptance, you have to consider 2 very important risks. There's producer's risk. That's the risk that you, as the operator or customer, might wrongly reject a perfectly good component or system just because of natural statistical fluctuations in the observed data. Bad luck on the day. And then on the flip side, there's consumer's risk, that's the risk to you, the operator, of wrongly accepting a faulty component or system that actually doesn't meet your specified reliability requirements. Bad luck again, but in the other direction. Balancing these 2 risks is absolutely crucial for fair and effective contracts.
And for you, the engineer on the ground or the project manager signing off on these systems, understanding the variance and statistical certainty of your MTTF measurements is absolutely vital. For the Poisson distribution, there's a remarkable and very practical result. Its variance, which measures the natural spread or dispersion of your data, is uniquely equal to its expectation value itself. So sigma squared equals mu. Amazing, right?
It's quite elegant, yeah.
This means the natural spread of your measurements, your standard deviation, is simply the square root of mu. So if you expect new failures, you can generally expect your observations to fall within the range of mu plus or minus mu, roughly speaking.
This simplifies things immensely for failure number analysis and helps set realistic expectations. It tells you directly that the precision or statistical certainty of determining the true failure rate depends directly on the number of observed failures you manage to collect. Let's take a concrete example. Imagine you're trying to demonstrate a specified MTTF of 100,000 hours for a particular control circuit. If you have 16 such controllers installed across your train fleet and your demonstration period is 3 years, you'd statistically expect about 4 failures. But here's the kicker. With only 4 expected failures, your standard deviation is 2. Your statistical precision for a single observation period might only be plus or minus 50%, 2 out of 4. This means you could observe anywhere from 2 to 6 failures, and it would still be well within the natural statistical fluctuation for a system that is meeting the 100,000-hour NTTF target.
Right. And this is a common pitfall in transportation projects, isn't it? We often find specifications demanding a precision of, say, plus or minus 10% on an MTTF measurement, when the expected failure statistics simply don't support it for the given number of components and test duration. You might need, 100 observed failures to get that kind of precision, but you're only expecting 10. In real-world transportation, the actual numbers of failures for a single component type during demonstration periods are rarely high enough to permit determinations with a relative error lower than, say, 20%, sometimes even higher. So it's not just about what you want to measure, but what you can realistically measure and prove with statistical confidence given the circumstances.
That's a crucial point. So, while the Poisson distribution is excellent for discrete counts of failures telling us how many times we expect something to happen, engineers often need a continuous way to set precise confidence intervals around those observations. That's where the chi-squared distribution comes in. Now, the underlying math behind its connection to the Poisson distribution involves something called degrees of freedom, and it gets a bit technical, but the practical takeaway is far more important for us here. The chi-squared distribution provides a continuous, smoother lens through which to view those discrete Poisson counts. It allows engineers to set any desired confidence interval for their failure numbers. It lets you say, essentially, based on our observations, we are 90% confident that the true underlying failure rate of this component is between value X and value Y.
Okay, so this might sound a bit theoretical, but the practical upshot is powerful for you, the engineer or manager. It gives you much more granular and precise control over interpreting your observations. For example, if you've observed, say, 7 failures from a component in an experiment or a demo period, you can use the chi-squared distribution, often through specific pre-calculated tables or software, to determine, say, the 80% confidence interval for the true underlying failure rate. These tables provide multipliers that help you calculate the lower and upper limits within which the true value is expected to lie with that 80% confidence. It's how you bridge the gap from a simple observed count to a statistically robust range for reliability, giving you a much stronger basis for decisions and contractual discussions.
All right, so with these statistical foundations, hopefully reasonably clear, we can now look at how reliability parameters are actually measured, demonstrated, and accepted in real-world railway projects. This is where the rubber meets the rail, so to speak, putting the theory into practice.
Exactly. This is where theory meets practice, and potentially millions of dollars are on the line.
Yeah.
All the robust schemes used today in transportation projects, they really respond to these constantly emerging pragmatic questions. What can we realistically expect in terms of typical failure numbers and resulting MTTFs given our demonstration periods and the sheer count of components involved? With what statistical certainty do we demand to accept or reject measurements against our precise specifications? How good are our initial hypotheses for these expected values? Are they just guesses or based on solid historical data? And crucially, what levels of producer and consumer risk are truly acceptable for both the supplier and the operator? Do we only account for the supplier's risk, or do we need to balance that with the operator's risk too? It's a whole framework, really, and it actually bears a strong resemblance to established standards like the U.S. military handbook MIL HDBK 781, which has been a kind of gold standard for reliability test methods for decades.
Most reliability specifications in transportation today are still based on MTTF requirements for critical components. These numbers are often derived from existing historical data from similar systems, robust supplier information maybe from testing, or benchmarks from previous projects. Now, the critical point is that the obligation to demonstrate that the built system is consistent with these specified reliability values must be performed within a very limited period after system implementation, usually just a few years of operation, certainly not a decade. Often, these demonstration periods don't even extend beyond the initial warranty periods, perhaps 3 years at most. To give you a feel for what kind of numbers we're talking about, for a typical subway line, you might expect somewhere between 1 and 25 service-relevant failures for a particular component type over a 3-year demonstration period, rarely zero and rarely hundreds for a single type. So when engineers design these programs, they anticipate working within this fairly tight range of expected failures.
And it's crucial to recognize that even these numbers scatter significantly, right? Especially for those lower counts. And we're talking about statistical distributions, remember, so there's always a natural variation. You might expect 5 failures, but see 3 or 7. That's why an adequate acceptance plan needs to account for this inherent statistical variability. A very useful concept here is the discrimination ratio, D, which is defined as MTTS0 divided by MTTFL, where MTTF0 is your specified target reliability, what you ideally want, what's in the contract. And MTTFL is an unacceptable lower limit, a level of performance that you actually cannot tolerate, the bad level. For transportation projects, an adequate discrimination ratio is typically around 2, meaning you want to be able to statistically distinguish with reasonable confidence between your target performance is twice as bad. If your system is actually twice as unreliable as specified, you want your test plan to be able to detect that.
Okay, now let's look at the different types of acceptance plans commonly used. Fixed duration acceptance plans are a very common approach, perhaps the most common. These are typically employed when a supplier has credible historical data or robust predictions for their components' reliability, and the main goal is simply verification, confirming that the observed performance in the field aligns with the specified MTTF. It's about checking consistency, generally not about discovering an unknown MTTF from scratch.
Right. And the simplest version of this, and maybe the most tempting because it looks easy, is what we might call the fixed duration acceptance plan without specific risk agreements. It's pretty straightforward on the surface. You run your test for a set time, maybe 3 years, and you expect a certain number of failures, let's say 9, over that period based on the specified MTTF. The rule is simple. If you observe less than or equal to 9 failures, KCSE, you accept the system. If you observe more than 9K, you reject it. It's popular because it's easy to explain. However, and this is a crucial flaw for high-stakes projects, it leads to roughly a 50% chance of wrongly rejecting a perfectly good component just due to normal statistical fluctuations. That's a very high producer's risk. 50% of the supplier, which they won't like. Exactly. And equally problematic, it carries about a 50% chance of wrongly accepting a component that actually has a higher failure rate than specified, which is a significant consumer's risk, till 50% for you, the operator. So while it feels intuitive, it's statistically pretty inadequate for mission-critical systems.
To improve on that, we introduce fixed-duration acceptance plans with specific producer risk. The idea here is to explicitly allow for some statistical fluctuation in the measured failures, primarily to protect the supplier from unfair rejection. You set acceptance limits based on a pre-agreed confidence interval, usually favoring the producer. For example, if you expect 9 failures, but you're willing to accept a 20% producer risk, a quality equals 0.2, meaning there's only a 20% chance of unfairly rejecting a good component, you might look at the Poisson distribution and find that you should allow for up to, say, 11 observed failures before formally rejecting the system. This acknowledges the inherent statistical spread and effectively limits the financial and reputational risk to the supplier, making the contract more equitable from their perspective.
Okay, that's better for the supplier. But then the gold standard, at least in theory, is the fixed duration acceptance plan with symmetric producer and consumer risk. Imagine that tug of war again between the supplier and the operator. The supplier wants to make sure their good product isn't unfairly rejected, low payer, and the operator wants to make sure a bad product isn't unfairly accepted, low PEL. This symmetric approach is about finding that perfect middle ground, a specific failure threshold, where both sides agree to an equal small chance of being wrong, maybe 10% or 20% risk for both. It's like drawing a line in the sand, knowing that on either side there's a carefully calculated minimal chance of an unfair outcome for either the one who built it or the one who's buying it.
It sounds ideal, doesn't it?
It does. You're trying to find an acceptance-rejection boundary, a specific number of allowed failures, where 2 Poisson distributions, one for your specified MTTF, the good one, and one for an unacceptable MTTF, the bad one, maybe half the MTTF, essentially touch or overlap only within those agreed-upon balanced risk levels. This is the theoretical holy grail of acceptance testing, but it's also the most mathematically complex to define up front. It often leads to a don't-know gap, Where the observed results are ambiguous, they don't clearly accept or reject either hypotheses. Or you could even get situations where theoretically both the good and bad hypotheses could be rejected based on the data. It requires careful approximation or more advanced calculation methods to define those precise, discrete acceptance rejection numbers upfront in the contract.
Hmm. Building on those fixed duration plans, we also have sequential acceptance plans. This is a more dynamic and in some ways maybe more intelligent approach. Instead of running a test for a fixed duration and then making a decision, you can continue testing and analyzing data in real time or perhaps at set intervals. You keep going until a clear acceptance or rejection decision can be made with the desired statistical confidence. The core idea is that you're continuously calculating the probability ratio, essentially, the likelihood of your observed failures coming from the good distribution, your specified target MTTF, versus the bad distribution, an unacceptable performance level.
The benefits of this approach can be really significant, especially for you in the field. For one, it has the potential for earlier termination than fixed duration tests. If a system is performing exceptionally well, or maybe exceptionally poorly, you might reach a statistically significant decision much sooner, which can save a lot of time and money on demonstration. It offers great flexibility, particularly when initial results are ambiguous or fall into that don't know zone of a fixed plan. Instead of being stuck, you can simply keep collecting more data until the picture becomes clear. It can also be used to subdivide a total demonstration period, say 3 years, into multiple shorter intervals, like yearly check-ins or reviews. This is particularly valuable because it allows for second and third chances for suppliers. If they experience some initial infant mortality issues in their equipment, which is quite common,
Very
they
common.
can implement remedial actions, fix the problems, and then restart a new test interval, demonstrating improvement in subsequent periods. It kind of fosters collaboration and continuous improvement rather than just a pass-fail judgment at the end.
That's true. However, the challenge with sequential plans is that they require more upfront preparation. You need predetermined tabular or graphical test plans specifically designed for each individual MTTF requirement and risk profile, error and VATA values. It's not a generic chart you can just quickly reference. Each scenario needs its own carefully calculated sequential plan. This means more work in the contracting and planning phase, definitely.
Okay, so those are acceptance plans deciding if something meets a pre-agreed standard. But beyond just accepting or rejecting a hypothesis, sometimes the objective of a program is simply to measure the actual MTTF of a component or system in the field, and then check if that measured value is consistent with what was specified. How do we do that?
There are two primary methods for actually measuring MTTF. The first, and overwhelmingly most common method in continuous operations like railways, is determination upon time. This method is based on a set of components operating for a fixed duration, for instance, 3 years. Crucially, any component that fails during this period is immediately repaired or replaced and put back into service, continuing to accumulate operating time. You don't just leave it broken. The measured MTTF is then simply the total accumulated operating time of all components, the sum of all their uptimes, including the time after repairs, divided by the total number of failures observed during that entire fixed period. This is what you generally see in continuous railway operations because, well, you need the equipment to be quickly restored to service to maintain operations.
Makes sense. The second method, less common but maybe insightful for certain specific tests or component types, is determination upon failure. Here, components are not repaired after failure. Instead, the test continues until a predetermined number of failures, let's say R, has occurred, and then the test stops. For example, imagine you start a test with 6 identical control modules. You observe the first failure at 12,350 hours, the second at 22,875 hours, and you decide to stop the test after the third failure, which happens at 30,250 hours. Since the failed components weren't repaired, only the unfailed ones continue to accumulate time beyond their failure point. To calculate the MTTF, you'd sum the operating time of the components that didn't fail by the test's end. For example, 3 components ran for the full 30,250 hours each, plus the time accumulated by those that did fail up to their specific failure point, 12,350 plus 22,875 plus 30,250. It gives you a clear measure of mean time to failure without the complexity of repair times influencing the uptime calculation. But as you can imagine, in a real railway, you can't just let things stay broken. So the upon time method with repairs is far more practical for maintaining service.
Absolutely. And Once you have that measured MTTF value from either of these methods, you still need to understand its statistical confidence. How certain are you about that number? You use those same chi-squared MTTF multiplier tables we discussed earlier to determine the confidence interval within which the true underlying MTTF is likely to be found. For instance, if you observe 9 failures during your test period and calculate a measured MTTF of 50,000 hours, you can use the multipliers from the table to state with, say, 80% or 90% confidence that the true MTTF of that component type actually falls within a specific range, maybe between 35,000 and 80,000 hours, for example. This helps you understand the reliability of your measurement itself, giving you a precise range for the real performance of the system, not just a single point estimate.
So if we briefly compare these different acceptance test plans, the simple fixed duration, those with specific risks, the symmetric risk ones, or the dynamic sequential plans, and also the MTTF measurement approaches, it's clear that while the numeric acceptoric limits might end up being surprisingly similar across some of them, their meaning, and crucially, the effort required to prepare and execute them, vary significantly. For many railway projects, particularly in medium complexity systems like a typical subway line, it seems fixed duration plans that incorporate consumer risk, or simply relying on MTTF determination within an acceptable confidence limit like 80%, are often considered sufficient. They strike a good balance between statistical rigor and practical real-world implementation, providing enough confidence without bogging down the project with excessive testing or overly complex contractual agreements.
Okay, let's shift our focus now. We've talked a lot about individual components and their reliability. Let's zoom out to the big picture. Availability in action from the operator's perspective. The many reliability values, MTTFs, of individual pieces of equipment within a transport system are somehow aggregated into a less technical, much more relevant availability characteristic for the passenger and the system operator. As we already defined, availability A is that ratio of average uptime to total time using MTTF and MTTR, MTTF, MTTF plus MTTR. And remember, this model formally assumes constant failure and repair rates.
Right. Now, how do you actually combine these values for truly complex systems, like an entire train or an entire signaling section, or even a whole line? It depends entirely on how the components are configured, how they work together. For serial configurations, imagine two absolutely essential components, maybe like a primary and secondary braking system control unit on a train, where both must be available and functioning perfectly for the train to operate safely. If just one fails, the whole system effectively fails from an operational perspective. In this scenario, the system failure rates actually sum up. A system equals 1 plus 2. And the system availability for that chain of components is the product of their individual availabilities, the system A1, A2. This means that even small individual unavailabilities can multiply quickly to a larger system unavailability. So if you have 10 components each with 99% availability, 1% unavailability in series, your overall system availability is only about 90.4%. You have to be incredibly careful when critical components are arranged in series.
Very true. On the other hand, for redundant or parallel configurations, the system remains available as long as at least one of the components is working. Think of duplicate control systems on a train, maybe two identical communication modules, where if one fails, the other immediately takes over without any interruption to service. These configurations significantly improve availability because the system only fails if all redundant paths fail simultaneously, which is much less likely. In this case, the system unavailability is the product of the individual unavailabilities. U system equals U1, U2. So two highly available components in parallel result in extremely high system availability. For example, if two components each have 1% unavailability and 99% availability, in parallel, the system unavailability is only 0.01%. 1% times 1%, giving you 99.99% availability, a massive improvement. And we can also model more complex configurations like 2 out of 3 systems, common in safety applications, where at least 2 out of 3 components must be functioning for the system to remain available. The math gets a bit more involved, but the principle is the same.
Okay, so serial multiplies availability down, parallel multiplies unavailability down. To visualize, analyze, and even optimize these complex interactions, engineers frequently use reliability block diagrams, RBDs. These are incredibly common visual and analytical tools in railway projects, especially for theoretically predicting and optimizing system availability during the design phase. An RBD essentially lets you model the system's architecture, showing precisely how components are arranged in serial or parallel relationships. It looks like a flowchart of reliability. Then, using those individual component MTTS and MTTRs, you can calculate the overall availability step by step, combining blocks according to the serial parallel rules. It's like building a Lego model of your system's reliability block by block.
Exactly. For example, an onboard train control configuration, which is a highly complex piece of equipment, might consist of dozens of filter cards, power modules, CPUs, communication interfaces, sensors, and so on. Each of these individual components has its own specified or predicted MTTF and MTTR. Through a detailed RBD analysis, all these individual RAMS values are aggregated following the serial and parallel paths to give you a system MTTF for that entire onboard controller. Maybe it comes out to something like 10,000 hours.
And this is where it directly connects to your experience as a passenger or operator and why these numbers matter. Even an MTTF of 10,000 hours for one train's control unit sounds pretty good, right? That's over a year of continuous operation.
Seems okay, yeah.
But if you have 20 trains in your fleet, each with that same 10,000-hour MTTF controller, that means you'd statistically expect an unavailability event related to an onboard control unit somewhere in your system every 500 hours. 10,000 hours, 20 trains. 500 hours is roughly every 3 weeks. Suddenly, that good MTTF translates into fairly frequent system-level events. This is precisely why these aggregated RBDs are so crucial. They help identify hidden strengths and critical weaknesses in the system architecture and pinpoint the major unavailability drivers, the components or subsystems contributing most to potential downtime long before metal is cut or concrete is poured. RBDs are also extensively used to estimate overall system availability by combining partial RBDs from different domains like rolling stock, signaling, power supply, and even station equipment like platform doors or elevators, giving you that holistic view of the entire railway operation.
That's the theory, and it's powerful for design. However, while RBDs are excellent for technical prediction and for allocating reliability budgets to suppliers during the design phase, they often fall short when it comes to reflecting operational reality accurately. Why? Because they tend to assume that every failure impacts the same number of passengers or has a linearly equivalent operational impact, which is rarely true in a dynamic railway environment. A platform screen door failure at one station, for instance, might cause a temporary localized delay, maybe requiring manual operation, but a critical train positioning system failure could potentially halt an entire section of the line, even if both components have similar technical repair times, MTTRs. The consequences are vastly different. It's also incredibly difficult, sometimes impossible, to accurately measure precise restoration times, and especially their complex consequential effects, like knock-on delays, across thousands of diverse events in real-world operation. You can't just stop a busy train line and perfectly measure every ripple effect of a minor fault.
Exactly. This is why there's a strong push, especially from operators, for more operationally relevant metrics beyond just those abstract technical availability percentages like 99.9%. The sheer diversity of system failures. I mean, from false alarms that just need a quick reset, to onboard control unit shutdowns requiring a technician, to a physical door simply refusing to open or close, and the equally varied remedial actions. Like remote resets from a control center, on-site staff intervention, maybe even rerouting traffic onto different tracks. It creates an incredibly complex web of potential scenarios and impacts.
The solution, or at least a very pragmatic approach, is to organize these highly diverse MTTRs and failure impacts into a finite, manageable set of failure categories based on typical operational responses. This requires a specific, detailed operational analysis up front to understand what actions the operator's failure management team would typically plan and execute in response to different types of incidents. For example, a common and effective approach uses three broad categories. Category 1C1 for remote recess or very minor issues resolved quickly, typically less than 5 minutes, with an average response restoration time of maybe 3 minutes. Category 2C2 involves on-site staff intervention, maybe taking 5 to 20 minutes, with an average around 13 minutes to resolve. And Category 3C3 covers longer durations, say over 20 minutes, which are severe enough to potentially lead to reduced traffic schedules, significant rerouting, or even temporary line closures in the worst case. And it's really important to stress that the operator's failure management structure, where staff are located, their response times, their level of training, the tools they have, significantly influences how these categories are defined and how quickly incidents in each category can actually be resolved.
Okay, so you group failures by how you typically respond. And once you have these categories, the real challenge becomes quantifying the actual impact on the service. How do you find a common denominator for the effects of an event that accurately accounts for those ripple effects, like trains bunching up or delays cascading down the line? A really practical, discrete metric that cuts through this ambiguity is lost departures, or sometimes called lost missions. Instead of trying to sum up vague delay minutes that might not truly reflect passenger discomfort or operational chaos, you simply count how many scheduled train departures are effectively lost, are significantly disrupted due to an incident.
Yeah, this lost departures metric is quite powerful. Traditional delay minutes can be misleading. A 5-minute delay on one train might ripple into 50 minutes of cumulative delays across a whole line, affecting hundreds of people differently. Lost departures tries to cut through that ambiguity. It's a more direct measure of operational disruption. How many chances for a smooth journey effectively vanished from the schedule or were severely compromised due to an incident? It forces everyone from the supplier providing the components to the operator managing the service to focus on the tangible impact on the passenger experience, not just abstract technical uptime.
Right. Let's illustrate this maybe. A short C1 delay, say 3 minutes, in off-peak traffic where headways, the time between trains, are maybe 10 minutes, might only lead to about 0.3 lost departures. One train slightly delayed, not a huge deal. But that same 3-minute delay in peak traffic, with tight headways of maybe 2.5 minutes, can quickly lead to 1.2 lost departures because trains immediately start bunching up severely behind the initial delay, creating a cascading effect.
Exactly. And for a longer C2 event, say a 13-minute delay in peak hour traffic, that can rapidly escalate. You might see 5, 10, even 15 lost departures as multiple trains pile up, creating huge gaps and then surges in service.
And these departures aren't truly lost in the sense that the trains will eventually run, maybe.
Yeah.
But for passengers, that first severely delayed train is packed to the absolute gills, while subsequent bunched trains right behind it might be virtually empty. From the passenger's perception, it's equivalent to lost trips, lost capacity, and a massively degraded service experience. It feels like chaos.
Absolutely. And sophisticated system simulations, often developed at technical universities like TU Dresden in Germany, for example, are used to model these complex operational impacts more accurately, feeding directly into defining these lost departure targets and understanding the real consequences of different failure categories. Now, the major advantage of this approach, defining and categorizing delays in this operational way and using a metric like lost departures, is that it effectively disentangles failure rates, the MTTF side, which are primarily the supplier's responsibility, from restoration times and the resulting operational impacts, the MTTR and consequence side, which are largely the operator's responsibility to manage. This clarity allows the overall availability requirement to be translated into something much more concrete, a set of acceptable failure or incident numbers per time interval for each specific category, C1, C2, C3, etc.
Okay, so how does this actually work in practice, in a contract or a project? It starts with defining those failure and consequence categories, like C1, C2, C3, and a clear metric like lost departures.
Mm-hmm.
Then a delay spectrum is defined. This is essentially a comprehensive table agreed upon contractually that outlines the maximum acceptable number of incidents per year, or per month, or per quarter, for each specific delay category, how many C1s are okay, how many C2s, how many C3s, before penalties kick in or acceptance is withheld. Now, to make the spectrum work, you need a high-level system FMEA, failure mode and effects analysis, done beforehand.
That's critical, yes.
This FMEA is a meticulous process that links every potential subsystem failure, like a door failing, a signal failing, a communication link dropping, to its probability of falling into a specific delay category, C1, C2, C3, etc., and its resulting impact in terms of lost departures, for example. This detailed analysis directly yields the expected consequences of different types of failures in their correct proportions, which allows for top-down target allocation and, crucially, the budgeting of unavailability across the entire system. You're not just hoping for the best, you're planning for inevitable failures and managing their impact proactively.
And when it comes to demonstration, proving compliance with this delay spectrum, there are typically 2 key levels involved. First, there's the paper demonstration, before anything is even built or installed sometimes. Suppliers must show, through their detailed RBDs and the system FMEAs, that their equipment is theoretically likely to meet the required delay spectrum. This means their calculated failure rates for individual components, when distributed across the defined delay categories based on the FMEA, must not exceed the allowed numbers specified in the spectrum table. It's a theoretical but vital proof of concept and design validation. Secondly, and perhaps more importantly operationally, there's the field demonstration. This happens after the system is fully commissioned and running in passenger service. This demonstration simply becomes a matter of meticulously recording the actual event numbers that fall into each delay category, C1, C2, C3, in real operation. You're counting incidents, not trying to measure every single complex restoration time or consequential delay minute. These field demonstration periods often span multiple years, maybe 3 years total, but broken into yearly periods for reviews and assessment. If a period fails to meet the spectrum targets for one or more categories, a new test period may begin, typically only after the supplier implements agreed upon remedial actions or improvements to address the shortcomings. Final acceptance of the system usually requires consecutive successful periods, showing sustained performance that meets the operational requirements defined by the delay spectrum.
This approach sounds like a true game changer, actually. It minimizes ambiguity in interpretation, which must plague simpler percentage-based targets. And it clearly divides responsibilities between the supplier, providing reliable gear, and the operator, managing failures effectively. It really zeroes in on the real-world impact that passengers and operators feel most directly. Delays and disruptions count in a tangible way. It's about making the abstract world of statistics translate into a tangible, reliable journey for everyone using the system.
Absolutely. Ultimately, while some operators still rely on more straightforward percentage availability targets, for example, maybe specifying 99.9% overall system availability, sometimes broken down by fleet availability, station availability, or travel delays, the delay spectrum approach offers significantly less ambiguity and a clearer, more objective accept-reject process within contracts. However, it does require more upfront failure management analysis and a greater capacity and commitment to track detailed unavailability effects and categorize them accurately from the operator side. It's more work initially, but potentially clearer in the long run. The best choice truly depends on the operator's specific needs, their internal capabilities for data tracking and analysis, and their preferred level of contractual clarity and risk sharing when dealing with these complex, multifaceted railway systems.
Wow. We've taken a real deep dive today into how statistics isn't just, theoretical math tucked away in textbooks when it comes to RAMS and railway projects. It's the absolute bedrock for designing incredibly reliable systems from the ground up, for agreeing on crystal clear contractual terms between suppliers and operators, and ultimately for ensuring the operational availability that keeps our cities moving safely and efficiently. We've journeyed from those abstract definitions of uptime and downtime all the way to tangible impacts like lost departures and the complex choreography of managing system failures using tools like delay spectrums.
It's quite a journey, isn't it? So maybe next time you're comfortably riding on a train or subway, take a moment to think about that hidden layer of statistical precision and sophisticated planning that goes into every smooth journey you take. It's a continuous, complex dance between those statistically unlikely failures and the engineered resilience that anticipates and mitigates them, turning potential chaos into predictable efficiency most of the time. And a thought for you. As you embark on your own engineering projects or delve deeper into railway safety or systems engineering, what surprising statistical challenges might you encounter in ensuring reliability in your own field? Perhaps in software development reliability, or even something seemingly simpler like managing a restaurant, a complex supply chain reliability. The principles apply broadly.
That's a great point. Hopefully this deep dive is giving you a fresh perspective on the invisible frameworks that quietly keep our world moving day in and day out. Until next time, keep digging, keep learning, and keep asking those big, fascinating questions.